You're probably familiar with the idea of diffraction from GCSE physics. So the way we describe this is the spreading out of a wave after passing through a gap. So we've looked already at representing waves with this wavefront idea. So remember, each one of these lines could be the peak. So let's say peak to peak, so the gap between these two lines is the wavelength of the wave, and the wave moves towards a gap and then spreads out. So we get this maximum effect of diffraction, as shown here, when the wavelength is approximately the same size as the gap that the waves are passing through. If we increase the size of the gap, we get a reduced amount of diffraction. So we still get diffraction, but it's not quite as much. And then the bigger the gap, well, it starts to almost diminish to zero. Most of the wave just goes through unchanged. We get a little bit of diffraction at the end. So generally speaking, in physics A level, we're talking about waves passing through a gap. We also get a bit of this effect when waves pass around an object, which is comparable size to the wavelength, and then that wave will bend around the edge. Lots of examples and applications, so CDs or DVDs reflecting all the colours of the rainbow. That involves diffraction. We get a red colour during sunsets. A spectrometer, which we might look at later on in this topic, separating white light using a prism, holograms, light bending at the corner of doors, X-ray diffraction. So this is used a lot in science and research, and there's a lot of examples of this in the real world as well. So the principle of superposition, this is something that you need to know for the exam. When two or more waves meet at a point, the resultant displacement is the sum of the displacements of the individual waves. So we normally talk about this when two coherent waves meet. So if we have coherence, then the two waves are identical. They have the same frequency and the same wavelength. However, the definition we use for coherence is two waves with a constant phase difference. So that might be a constant phase difference of 0 if they start at the same point, or 180 degrees if they start half a wavelength out, but there is no change in that phase difference. So very often coherent waves are produced by the same source. So for example, you might have two loudspeakers both connected to the same signal generator, and the waves are coherent as they're produced from the loudspeaker. So the two extreme scenarios, and the ones we generally talk about, are constructive interference and destructive interference. So if the two waves, both coherent, meet in phase, which means their phase difference is 0, then they add up to make a wave which has got twice the amplitude of the original wave. So the amplitude increases. The other extreme is if the phase difference is 180 degrees, so anti-phase, and then they cancel out effectively. So if we have a peak meets a trough, that cancels out to give 0, trough meets a peak, and so on. So these are the two extreme cases, but we do get superposition even when the waves are not coherent. And this is used in synthesizers to produce complex sounds, artificial wave sounds, which the brain thinks is a trumpet or an acoustic guitar or whatever it might be. And we can add multiple waves together of different frequency and amplitude and phase difference to make far more complex waves. We're going to talk about an example of the principle of superposition, which you may well have seen demonstrated in a science lesson, and it's often talked about in exam questions as well. So it's quite an easy one to set up. You could probably do this yourself at home if you want to. You need two loudspeakers, both connected to the same source, and we normally just use a simple sine wave of a particular frequency. So it's a pure sine wave, a particular frequency being produced. So if a person walked along in front of these two speakers, what they would hear is a series of loud and quiet sounds. Now, it wouldn't be totally quiet because you've got a lot of reflection around the room, but what is effectively happening is where those two waves, so the wave from the left speaker and the wave from the right speaker, where they meet in phase, we get constructive interference, so we hear a loud sound, and where they meet out of phase, we get destructive interference, which is a quiet sound. So we need to be able to explain this in terms of path difference, in terms of how many waves have actually travelled. So this is a side view, or maybe a top view, of what we've just talked about. So we've got two loudspeakers. They're both producing the same type of wave, a coherent wave. So if you're in the midpoint of these two loudspeakers and you stand here, you will hear a loud sound. If we look at the number of waves, we've actually got 5.5 waves have travelled from this speaker here, and 5.5 waves have travelled from the speaker at the bottom. So they started off in phase, they've travelled the same distance, so their path difference is 0. So they're in phase with each other at this point. So we'll get constructive interference, we'll get maximum amplitude, and we'll hear a loud sound at this point. If we consider a point as shown here, which is in front of one of the speakers, so we have the same wave format as we had previously from the one at the top. The one at the bottom, these waves now have to travel a little bit further. So they've travelled a greater distance, so they're no longer going to be in phase in this particular example. And if we count how many waves here, we've got a total of 7 full waves compared to 5.5 waves. So we have a difference of 1.5 waves. The path difference is 1.5 waves. So now these two waves are going to meet out of phase, 180 degrees out of phase, known as antiphase. So here we get destructive interference, and effectively the waves cancel out and we get no sound at all.